Okay, so we were talking about tectonic movement as part of the third phase of planetary surface evolution. And we were talking about the fact that Earth is like Goldilocks, it's just right. And we went through and checked off all the things that Earth had that made our crust break and break into plates that could drift over hundreds of billions of years across the surface of the Earth. So let's go into that a little bit more specifically because it's fascinating stuff. When you have plates such as you notice here, and what I'm saying is that you can even trace the lines, and this is the Pacific plate, which is in the middle here, a big one. There is a North Atlantic plate which bridges right onto the Pacific plate and comes out right along here along this ridge. There's a South American plate which starts right at the Andes and goes out through the Atlantic. There's an African plate, there's an European plate, there's an Asian plate, and there's more than that. When these plates pull away from each other, that's called a divergent boundary, where they pull away from each other. And some of the geological formations that you'd note with that are rift valleys. These rift valleys can fill in. For instance, the Red Sea is a perfect example of a line formed when the African plate is breaking away from the Arabian plate. And you will also see these rift valleys. Well, they're actually ridges in these areas that are in the Atlantic Ocean, the mid-ocean rise, and they are in the Pacific here, the mid-ocean rise. Now you might say these are not valleys, but this is an area where the plates are moving away and the magma is coming in and forming a rise in that area. These divergent boundaries were actually the first things that were seen by geologists to let us know that the Earth is made up of plates. They started to see that the rises in the ocean and the rift valleys in other places had younger rock along those areas. And they started to understand that this was the magma that was coming in and filling these basins and making these rises at this divergent boundary. To this day, the Red Sea has a very has pockets of hot springs at the bottom of the sea that are very, very hot, and they prevent most animal and fish growth in that area because that area is still pulling away and releasing the magma from underneath. So Earth is where you find these divergent boundaries. Earth is where you find the plates. It's the only area in the solar system where they are. These plates can also form convergent boundaries where the plates come together and one moves on top of the other and one goes down and one goes up. Convergent boundaries can also be called subduction zones, okay, like ductwork, that goes around your house. These plates can actually move around as well. They can go under, subduction. They can form mountain ranges such as the Appalachians, the Andes, the Himalayas, the Urals. Really beautiful line right there, right between the Asian plate and the European plate, and the Rockies, which is a convergent boundary as well between Pacific and between North American. Thirdly, your Earth is unique with these plates and the way they move, of course, and there's a very important one, the transform plate movement, which is a sliding movement forward and back. And you know what that is? That's the California San Andreas fault line. It is also a fault line in the Aleutian Islands. Now that could be considered a subduction zone, but most geologists will talk about a transform plate movement in the Aleutians. So it can go both ways, but most of them will talk about the sliding motion, and there is a bit of subduction associated with it. But there was recently an earthquake in Hawaii that was a transform event. Let's keep going on this. And we've been all through the Earth and tectonic movement. The Earth is the only place in the solar system where there is tectonic movement. On the other hand, there are two other ways to work with this third method of evolving planetary surfaces. Again, the third method is the slow surface evolution, and there's three ways to get there: tectonic movement and erosion and weathering. So we're going to go into erosion and weathering a bit now. Both of these require wind and water. Well, erosion is moving and eroding away land and rock. Weathering is breaking down the land and rock, but it stays where it's at, often seen in mountaintops. And so weathering and erosion both use the same processes in many ways to break down rock. It's just that erosion moves the rock. In order to have wind and water, you need to maintain an atmosphere. So that we're going to look into planets that may not have had tectonic movement, but maybe they can evolve their surface by using erosion and weathering because they may have an atmosphere. So let's go and look into that. If you need an atmosphere for the wind, for the air and the water that are associated with erosion and weathering, then you need gravity to keep that atmosphere around the planet. So let's explain that a bit. Gravity pulls air molecules toward the Earth, giving them weight on the Earth. And the weight of those air molecules pulling down all around us is called air pressure. I teach a class in meteorology and climate, talk about air pressure all the time. And at sea level, the pressure of the air that is on a square inch column that goes from Point Pleasant all the way to the sun is approximately 14.7 pounds per square inch. You may have heard that before. I don't use pounds per square inch. I don't like English. I use the English system of measurement. I like metric. I use the equivalent, which is 1,000 millibars. So you may hear about a hurricane coming through at 984 millibars. And you may hear of a beautiful day where it's at 1016 millibars. Right? It's a small gradient there, very important gradient. So gravity is essential to maintaining the atmosphere that provides the air and the water for the erosion that smooths the surface and the craters from bombardment. When we talk about this, we talk about gravity as having a hold on air molecules, which you can't see, but this hold by gravity is something that is very apparent at sea level, and then it quickly drops off at altitude. By the time you get to Mount Everest, you are at about 25% of the air pressure that you had at sea level. And when you are at about 17 kilometers up, about 9 miles, you have 90% of the air pressure for the Earth below you. So that you can see that when you're flying in an airplane, you're flying in very low air pressure. That means that there's less water vapor in the air at altitude, and there's less oxygen in the air at altitude, and every other gas that's there as well. The differences in temperature are also something that you're very aware of. When you're at Point Pleasant, the temperature is very moderate. When you're on the top of Mount Everest, the temperature is hellishly cold because there are not enough molecules in the Mount Everest area to maintain the energy to keep the air warm. So we've got a case where we need the right amount of gravity to keep the right amount of air and water vapor in around the surface of the earth in order to erode it. Differences in temperature, like we noticed from sea level to Mount Everest, actually cause winds for erosion. The differences in temperature actually cause condensation, which leads to the precipitation, the ice, the oceans, the waves that produce erosion as well, and weathering. So if you need gravity to maintain the atmosphere, then which terrestrial planets have gravity? Well, actually, they all have gravity. So you can go back to our comparative chart and they all have gravity. Every bit of mass has gravity, but it's the right amount of gravity. And so you might say to yourself, well, which terrestrial planets have a liquid iron core? And that gets you closer because that can be the right amount of gravity. We have Venus that has an iron core. We have Earth that has an iron core. And there's some talk that Mars must have had an iron core early. So we're going to go with that. And in talking about that, we can talk about the atmospheric evolution on Earth, on Venus, on Mars. The rest of the planets didn't, the rest of the terrestrial planets, Mercury, trying to think, yeah, we're talking Mercury, never did have an atmosphere. Mercury is too small to have gravity. It just doesn't have enough. And when it comes to forming an atmosphere based on the gravity that you have, you are talking about a timeline as well. At the formation of these planets, well, all planets basically had a primitive atmosphere at the start, even Mercury. It had a previous atmosphere of very, very light atoms, hydrogen, helium, a compound, methane, which is quite light. Ammonia is another compound, quite light. Water vapor, very light as well. These are volatiles, these are gases, and they're quickly lost to space. Water vapor is a gas. If you take my meteorology course, you'll learn all about how important water vapor is as a gas. But these were quickly lost to space very soon after the formation of planets because it's very hard for any gravity to hold in such light molecules. There's no mass to hold them in. So that we look at a secondary atmosphere and whether or not the terrestrial planets could secure a secondary atmosphere with heavier molecules and compounds. These are heavier, they're dependent on gravity now, and Mercury could not do that with the very small bit of gravity that it has. It could not maintain a secondary atmosphere. These heavier molecules were formed later from the mantle through all that magma coming up. So that magma brought in an enormous amount of sulfur dioxide, an enormous amount of nitrogen, carbon dioxide, and we now know that volcanoes produce the water vapor on Earth and the water vapor on Venus and on Mars. So let's start with what you know about atmospheres, and the next video is on the Earth's atmosphere, and then we'll go to Mars and Venus.